Okay. So I think I'm audible, right?
Yes, sir.
Okay. Thank you. Thank you. So let's share this. Yes. So good evening all. So today we would be having a brief introduction of the session based on the reactive power compensation, or we can say Bolt-Var control, and then we'll solve the assignments, numericals based on based on only this week's lecture that has been given by professor. So the need of Bolt-Var control, why it is required. If someone can please say something, if you want to say something, you can. What's the need of doing this World War control in the present operation and planning scenarios in power distribution system? Any idea that you have understood from the week's lectures? Anyone can please share, or otherwise I'll just give a brief introduction of this.
For the power factor improvement.
Yes, power factor improvement. Yes, definitely. And by improving the power factor, what benefit can we add to the distribution systems from the customer point of view or utility point of view?
Power loss minimize.
Yes, the aim is to minimize the power loss, but here the power loss is the objective. To minimize the power loss is the objective, but what is our aim to minimize? Actually, what we are trying to minimize, or we can say trying to maximize in the form of customers. From the customer's point of view, what is our aim in the distribution systems by mm, incorporating these gold bar control, or we can say active bar compensation.
Local supply of reactive power.
Hi, yes, we are supplying locally the reactive power, but what is it? What means after doing this, or as a result of this, what is actually getting improved?
Voltage is improved.
Yes,
Voltage drop.
voltage. Voltage is the main aim. To we have the limit, right? The limit which we have the set of predefined limit of 5% to 6% voltage drop, which can be ensured that it lies within that tolerance band, okay, plus minus. So that's our aim. The customer should get the proper their utility voltage, that the end point means there are the substation. If the customers are towards the substation node, they deliver means the voltage that is observed in the customer node, in the substation node or near to the substation node, are the voltages profile are quite good. But as we go deep down towards the end node, so there these problems can be observed, and the major aim is to improve the voltage profile, then for which we try to do the active power loss minimization as an objective function, and accordingly, we try to place the capacitors as per the system requirements, the uniformly distributed loading scenarios with concentrated loading scenarios. So all these things are much of an not much of an issue in the current context. So with this, that's the major aim. This mostly there are numericals that I have.
Sir, I have a one question.
Yes, yes, yes.
Uh, in distribution system, the capacitor compensation is using for the voltage improvement, but in transmission system, yeah, substation, we are using the capacitors. I think there is a main working for the power factor improvement.
Yes, power factor improvement is definitely the power factor is getting improved. Okay. Since we are, as we have seen the phasors from the phasors, the power factor seems okay. Let me just yes, definitely power factor improvement definitely observed. Let me just show in the from the phasor diagram as we can see that let's suppose here is our reference voltage and suppose we have a lagging current like this one. Okay, so if this is our voltage, initial voltage, and this is our initial current, and this was our angle theta, or you can say delta. So now if we have an additional capacitor which is delivering the, this is a inductive system. This is the phasor diagram for a inductive as well as resistive, means RL type of system with dominance of inductance. Okay. So now if we place a capacitor, so that will then it definitely draw leading current. Okay. So when we draw the resultant current, this will be our new power factor angles. Okay. Okay. So let this be delta 2. So power So power factor is definitely getting improved, right? So as per your statement, the power factor is getting improved, but here the main aim, as we have seen that with the placement of the capacitors, the voltage profile from the, let's suppose this is the substation end, and as we go down towards the end node, here are the loads being placed all throughout the network, and as we go down to the substation from the towards the very end, from the substation, this is the substation. So there, if we see that the voltage profile, if this is the voltage and let's say it is 1 per unit at the substation node. So as we go down, since there are voltage drops, right? IR and IXL. IXL, and for each of these sections, each of these lines, there are voltage drops, and as we go down towards the end node, we can observe that the 1 per unit voltage dips and maybe it may reach to zero point 0.9 per unit, but this is not permissible, right? So we'll have to maintain that voltage within that permissible limit of plus minus 5%. Okay, and in order to do so, we place the capacitors so that the voltage profile of the entire system gets a better shape. Okay, and this is for the current. So from the power factor point of view, the current is also getting improved. The voltage profile, as it was previously, the that voltage drop for each and every section, since we can see that this is the magnitude, right? And for this one, and this for this smaller one, we can see the current magnitude had diminished a bit, right? So the drop that is IR and IJXL, mostly the system would be inductive. Since the loads, induction machine and all these things, all this would lead to and okay, sorry, here I would be multiplied IJXL. So So ultimately we can see if this I value gets reduced, so that would lead to a minimization in the total voltage drop. And when it reaches to the rarest at the end, in the starting from the substation, so the voltage profile would at least get a better shape. It will not be 1 per unit, but at least we can try to make it near to 1 per unit or within that tolerance band, right? That's our aim. So that's the major aim. So I think I've tried to address your question. So if you have any queries, so power factor definitely is getting improved, as well as the current voltage drop, that is reducing, which is adding on to the improvement in the voltage profile. So that's the point.
Okay, sir. Thank you.
Okay. Okay. So okay, just let me start. So that's it. If you have anything, already the theory part has been covered and even numericals have been given in the assignment. So I've tried to take the numericals from the previous and last to last assignment, and we'll have a discussion. Some are, half of them are numerical and half of them are theoretical. So let's start with this week's assignment discussion part, right? So that will help you in doing this week's assignment and in the final exams too. So please go through this question, and in the meantime, the pencil is the charge of the pencil is not up to the mark. So please go through the question. There are 5 questions related to this. I think it's visible, right?
Yes, sir, visible.
Yes. So please.
Sir, one more question. The power factor is leading and lagging.
Yeah.
But capacitor, we don't consider the positive and negative. Yeah, what?
Power factor is leading or lagging in the sense. Can you please elaborate a bit?
That means if power factor value is positive,
Yes.
uh, uh, that means their capacitor is required, but its value is negative, then capacitor is in compensation is not required.
Okay. Okay. Just let me. Suppose you have. So you have a. Let's say you have a voltage here. Voltage phasor here, and for the capacitive current, what is the phasor for capacitive current? How it will lead or lag the voltage, reference voltage? If they are if in a system there are 3 equipments or 3 components: resistance, reactance, and capacitance. Reactance, sorry, not reactance, inductance and capacitance.
Inductor.
Inductance and capacitance. So for inductance, the inductive current would lag the reference voltage. Okay. So if it is a pure inductive circuit, so that won't be the case in practical scenarios, but let's consider that it is for the inductive reactance only, and for the capacitive one, the current would lead the reference voltage, okay, by 90 degree if it is purely capacitive. But these cases are ideal, and for the resistive, the current would be entirely in phase with the voltage, okay. So now if in our distribution system what we see is that, suppose this is a substation, and there these are the let's say this is a trunk node, and these are the laterals, okay. These are the laterals, and let's say this is the end node with a load connected, and here other this. So these are the laterals, and from the laterals there are loads connected here and there. So let's not go deep here. So what I'm trying to say is that all these sections consists of resistances and as well as reactances, right? Since these are conductors, so from the there are two parts, like from the substation, when distribution substation, there are primary distribution and secondary distribution. Okay, so secondary distribution is the part which delivers the power to our residential areas. So these lines would mostly these lines would comprise mostly of the resistances as well as the inductive reactances. Now the effect of capacitance is minimized in the distribution system, since the lines are not, the towers are not of that the distance of the lines are very short, with distance in the sense compared to when 200 kilometers, these distribution systems are of how much? It's very less. So that's why the charging capacitance, the shunt capacitance all throughout the line can be neglected here. Okay, and as a result, what we can observe is that mostly it comprises of the resistances and reactances. Okay, so When these two things, now coming to this phasor, when these two components comprising of, let's say that IC part is absent for the time being, right? Since the IC part is absent, so the resultant current would be resultant of R and L only. So this would be our resulting current, and this would be our power factor. So in power factor, there is nothing like positive power factor or negative power factor. Okay, so we generally state them as a lagging or leading. So lagging with respect to the reference voltage. So since this is our reference, so as we are going downward, so this is lagging. And if same case in the same context, if we move this side, so that would be leading. Okay, so when we are in the lagging side and we are violating the line constraints, means there, or the we can say the voltage limiting constraints for the system, and because for those the utilities that are more prone to face the penalties because they can't do these things now in the present context. So as we can see, this is the operating power factor angle, and this is the resultant current. We can say this is the resultant current. Now this is lagging, and as per your question, if this becomes leading, so when will it become leading? Only if the dominance of this IC that I have erased, if this IC value is more than this IL, then only the system may, or the current of this system may go in the upper part, means this part of the plane. So and the reason behind it is, now from this upper part, this quantity gets reduced from this upper part. So from the top, if we reduce, so this is the resultant part. So the resulting current would become IL minus, oh sorry, IC minus IL, because the dominance of C is L. So this is IC. Okay, but that won't be the case because the capacitive current, for installing this amount of capacitive current, so in such a case it would face the overvoltage, and the cost that would be associated would not be admissible as per the utility point of view, because we'll have to take, or we'll have to collect that amount from the customers itself. So, and the cost, as you can see from some of the numericals that we'll discuss today, the amount of cost that is being incurred to involve the association of the capacitances in the system is very high. So we can't generally do. So what we can do is that we can try to at least install some part, means a bit smaller amount of capacitance or capacitive current that will inject the capacitive current, and this will lead to the reduction of this, let's say this amount of current gets minimized due to the certain installation of capacitances. Let's say this is newer IC. So now the resultant current that is acting in the distribution system is IL minus IC. Okay, and this IL minus IC would lead to, considering the resistance being same, this would lead to an improved version of the power factor, as well as the magnitude of the current getting minimized, that would yield, or that would result in a better voltage profile in the system. Okay, so when we have a lagging part, we try to install the capacitive system or capacitive components in the system so as to improve the voltage profile. And mostly our systems are, all our systems are lagging in India. Considering Indian context, approximately 65% of Indian loading scenario is induction motor loads. Okay, 60 to 65 induction motor. And what we know is that induction motor is highly reactive or highly inductive equipment. And based on the load models we have in, let's say, we have various kinds of load models that Indian Power Grid tries to incorporate so as to get a better understanding of how the system loadings change. As we all sometimes back also we have came to know that each and every 5 years the load model gets updated for every area. Okay, so when the load model gets updated on such a delayed time frame, because each and every day the loads are getting evolved, means the customers are adding up to the system, and based on the customers the dynamics, because PVs, winds and all these things are renewables are getting mass penetration in the system. So the problem is that the system dynamic or the dynamic behavior of the system is rapidly changing, and for that the load models that we all know, there are various types of load models. I think you might have also heard the ZIP model, Z impedance, current, power. Means these loads, some loads are proportionate to the impedances, some are proportionate to the current, and some are to the power. And I think in this course also professor has taught. I forgot. So, and for the composite load model, composite load model, ZIP plus induction machine. These entire thing forms a composite load model where the parameters of the ZIP, means the impedances, current and power. In addition to the induction motor we have a large amount of parameters, right? The R and XL, as we know, the rotor side from the equivalent diagram. Okay, so we can observe that motor equivalent diagram. So in order to have an adaptive load modeling techniques in operation in the current power system framework, people are also trying to work on the composite load modeling techniques and understand that how the loads are getting changed. So here induction, my point was to emphasize on this induction motor type, because as you have asked that power load might be leading, so that won't be a case in India context, and in every context. Means system loads are mostly defined by induction motor, as the industries runs mostly on the induction machines. Okay, so the around 60 to 65% of the, or 70, you may say 65 to 70% of the loadings are defined by IM, induction machine, and these are mostly the loads that we use. Means here the ZIP, from the ZIP we may find a few of these or most of the equipments following these ZIP models, and except for the pumps and all these things which comes under the category of induction machine. So my point is that mostly the system would be inductive, or the prominence of inductive reactance would be more, and for that we need to, and to, means we may say that to benefit the customer voltage profile, we will try to install shunt capacitances in the system, and there won't be cases where we will have inductive loads, capacitive loads in the system, for which we try to uh, incorporate in reactors. But in transmission system, such situations with low loading cases occurs when, and for that shunt reactors or series reactors needs to be incorporated. But those are special cases, means special scenarios, but not in practical. So here, actual practice, the loads would be in lagging in nature. So you, I think the better word is to use the leading and lagging framework, and not the positive and negative, because those positive and negative terminologies are generally not used. Means might be there in some cases.
Yes, sir. Yes, sir. Negative, that means lagging, and positive, that means leading case.
I understood your analogy, but yes, that's what my point of I was trying to emphasize. I think you
Yes, sir.
clarified.
It's clear, clear, clear. Thank you.
Okay, okay, then let's move on to the assignment part, right? So we have good number of problems that we try. So three-phase distribution feeder is drawing 120 ampere to supply a lump load. The load power factor is 0.6 lagging. The ampacity limit of the conductor is 100, so 100 ampere. And the capacitor bank is to be set up at the load end to reduce the current at the ampacity limit, keeping the load demand intact. So load demand would remain fixed. The feeder length is 5 kilometers, and the feeder line parameters are these value resistances and reactances are per kilometers. And load end voltage is 11 kV. So question is, this is the statement, right? So let me write. There are 5 questions. So write this. Question 1 is, determine the active power demand of the load. This is the question. This is nowhere related to the capacitive placement. Just prior to the capacitor placement, it's just required. In this question, it's only to find out the active power demand of the load. So consider this as the prior setup of capacitor. You please try to solve, as in the meantime I'll draw the circuit. So when this is given, so always consider this as line voltage. I think you already know. So, so per phase voltage would become 11 by root 3 kV. When this type of information is given and nothing is mentioned, always consider this as a line voltage. So load power factor is given 0.6 lagging. Okay. So very easy. Any any idea of what would be the formula of finding out this? So since this is the three-phase power output required, so we can say from the line power formula is root 3 VLIL cos phi. So everything is given. VL is also given. Line voltage 11, 3. Current is given. power factor is also given. Just calculate and see whether what would be the value. So the answer is okay. This is the final answer. So I have the options. Is it fine? So okay then let's move on to the next question. Now statement remains the same. Okay, so let's determine so this is the question. Determine the load demand in MVA. The last question was to determine the power demand, active power demand, and this is for MVA, so apparent power demand. So you can use directly the previous outcome and incorporate the, this one to get the result. C. think it's correct. Yes, yes. So, so already we have the real power. So, let me say apparent power, SL, and we form of minimal cost file. And PL is 1374. So this is equal to 600. This is the right answer. Okay, any doubt?
No, sir.
Okay. Okay, so moving on to the next question. Next question is determine. Okay, so this is the question. Determine the capacitor rating in kVAR. Okay, so as per the question, how can we find the capacitor rating? What is the limiting condition? Can anyone point out what is the limiting condition here to find out the capacitor rating? Which point should be given more emphasis here?
Real power? This 100 ampere should be given emphasis because the ampacity of the conductor is 100 ampere and we are working with 120 ampere now. So this is the limiting condition. So 100 ampere is our aim. Okay, and for okay, let us draw the circuit once again. So this was our supply side. This was our supply side, and this is the resistance, reactance, and this is the load side. Okay. So what it has been mentioned that the capacitor bank is to be set up at the load end. So load end it is mentioned. So this is the R and JX. This is the supply. This is the load. Okay. And we are required to install a capacity bank or capacitor bank at the load side. Okay. So as to reduce the or improve the voltage profile. So already the current that was flowing here was 120. Now our main aim is to have a current of 100 ampere here, which was previously flowing as 120 ampere, but the load should take 120 ampere, right? So initial cases, for the initial case, yeah. So for initial case, considering 120 ampere, so QL was root 3 VL IL sin phi, and cos phi is given as uh, cos phi is given as zero point 0.6 lagging. So sin phi will be 1 minus, if you can do, it would become to 0.8. This would come to zero point 0.8. So just put the values here. So what will be the value of QL? QL would be root 3 into what is VL, 11 into 10 to the power 3. Current is 120 ampere. This was the required case. Okay. Now with okay, just multiply. In the meantime, if anyone has got the answer, you can write it in the chat box. B. Mm, yes, B is the correct answer. Yes, B is the correct answer. B is the correct answer. T 2.8. So let me quickly finish. 182.9.045. This is the KVAR. Okay. Or we can say 1829. And with the feeder limiting value, S, what will be S? S will be for the capacitor. Considering S, let the notation S be, so KVA applied to both the feeder and so S will become root 3 VL IL, and root 3 into 11 into 10 to the power 3 into IL is 100. So this value would come to root 3 into 11, 1905. 1905.25 kVA. Okay. So, so what we can see is that now, as per the active power, so previously we have calculated the active power 1371. So let's just approximate these values. So reactive power, required reactive power would become S square minus E square. So S we have calculated 1905 square minus 1371 square. This is 1371. 1371.784. Right, 0.784. So this whole square. So this much amount of reactive power will need to 1905 square minus 1371. 1321.8. So this is the kVAR. This is the kVAR that is required. So this is the kVAR which is being supplied by the feeder. Okay. So the remaining amount of this is the required one. So highlight. So this is the required one. This is the required one. 1829. So this much extra value needs to be taken up by the extra capacitor connected. So Q value. So Q capacitor would be Q line minus Q, this Q value, this Q. So Q line was 1829 something like this, 1829.05045. Let us not take that part. And 1321.8. So just 1829 minus 1321. 507. So 507 approximately. And this is the amount of reactive power that needs to be taken out, delivered by the capacitor, right? Determine the capacitor rating. So the answer is B. I think it's clear. If anybody has any doubt, please ask. Option B is correct. And in this case also option C was correct. Is it clear? Okay. So this is 507 kVAR that needs to be delivered by the capacitor based on the capacitor. So this is this should be the rating of the capacitor. So moving on to the next question.
So these are the options. Determine the power factor of the feeder after the capacitor placement. Already we have the values, so you just place the values. So power factor of cos phi, you can say, is based on the available values here. We can directly put the values and find out the power factor. One of the power factor value is R by Z, but we can't use it here because the load side values are eccentric. What is our another option? We have real power by apparent power. Real power we have calculated. Yes, 1371. This was our real power. Already we have calculated 1371.7, or you can say 1371.8, rounding up the value. And S is 1905. Here we have calculated S. This is the S value. So 1905. Just 0.72. And what will be the value? Sorry, not the value. Where what will be the operational property of this 0.72? Is it lagging or leading? Based on the system that we have shown, as we have obtained, what will be the value? Lead or lag? Yes. So this is correct. Any doubt? So can we move on to the next question?
Yes, sir.
So next question is determine determine the voltage drop. The options are
Okay, so these are the options. Determine the voltage magnitude of the feeder after the capacitor placement. Please try to solve it fast and in the meantime charge the principal. Charge is taking. C. Yes, C is the correct answer. C is the correct answer. Okay, so resistance per unit length is or per kilometer is given. R is 0.8 ohm per kilometer. So total R would be for 5 kilometer it is 4 ohm, and the XL values, the X value is also given zero point 0.8, sorry, zero point 0.6 ohm per kilometer. So XL would be 6 into 3 ohm. So combining these two, we will get what we can see as Z. Since we are trying to find out the magnitude, so we can directly use these two. So 4 square plus 3 square would give 5. This is 16 and 9 25. So this would be 5, 5 ohm. And the current, so after capacitor placement, the current would be limited to 100 ampere itself, because that's our aim to not so we should not exceed the ampacity limit of the conductor. So the current will be the load current, we can say line current, we can say 100 ampere after capacitor placement. So the total voltage drop would be I Z, considering this to be the magnitude. So this is 500. Any doubt? This is the answer. I think it's clear for everyone, right? Okay, so is it fine? So can we move on to the next question?
Yes, sir.
Okay. So this is a question. This is a theoretical type question. This question, more one. So the capacitor placement in a power distribution feeder to appropriate locations and appropriate sizes results in lower power loss, better voltage profile, capacity release of the feeder, and all of the above. Out of these, which one is correct?
All of the above.
Yes. So, so So the analytical approach shows that the best location in view of power loss reduction for a single capacitor bank for a distribution feeder with uniform load density is at the substation side, at the midpoint of the feeder, at 66.66% of the feeder length, or at the end point of the feeder. What are the points to be emphasized here? What are the keywords that should be emphasized here in this question? Can anyone please identify or highlight? Because same type of questions can be framed here. Some keywords needs to be specifically identified so as to get the result or get the answer of this question. So yes, one is uniform load density. Another one one is single capacitor bank. Okay, so just direct analytical approach. So as we have seen in the lectures also that the starting end, this is, if this is the substation end, C, yes, C is the, so if it is at the substation end and this is the last node. So in between there are multiple nodes, but let's consider the first and last. So if this is 0th position, this is the distance between these two, and we considered as L. So at any point, considering an any point in between, we can treat that distance from the substation node to this node as X. Okay, any random point. So that is the point which we need to find out. Okay, so already we know that for single capacitor, the last slide for single capacitor, the value of x1 will be 2 by 3 into 1 by 1 minus lambda, right? And for uniformly distributed load, since the load is uniformly distributed, UDL, so lambda will be 0 here. Now from here only we are getting the value of x, 7. So x in percentage, or we can say 66.67%. Is it clear? So this is the derived formula. Derived formula as sir has shown in the slide. The final x1 value can be last slide, I guess. Here, this is the, is it clear? N is 1, single capacitor placement, and what is lambda? But lambda is ineffective here because since to get the value of lambda, the I2 reactive current at the end of line segment and reactive current at the beginning of line segment, since it is uniformly distributed, the value of lambda won't have any effect, yeah, because it is uniformly distributed scenario. So the lambda value would be 0 here. So same derivation, same. This is 1. Okay. Now there is a similar type of question. I think if it is clear, then we have the next question. This is kind of similar, but a bit tricky in the sense that we need to pinpoint the keywords here. The analytical approach shows the best location in view of or loss reduction.
This is the question that the analytical approach shows the best location in view of power loss reduction for single capacitor bank with lump or concentrated load at the end of the feeder. So lump load is connected at the end of the feeder. So what would be the location here? That was uniform load. This is lump load. Lump load connected at the end of the feeder. Pretty similar. So when it is connected at the end of the feeder and lump load, so the value of lambda will be 1 here, right? And when the value of lambda is 1, so what is it indicating? So 1 by 0, which means infinity. So x should be at the furthest point from the substation. So what will be the answer? At the end point of the feeder. Similar question, just the lump load and this was the upper one was uniform load, UDL type. Okay. I, now we have the other question which is, it sounds similar. This is the question. Analytical approach shows that the best size in PU in view of power loss reduction for a single capacitor bank of distribution feeder with uniformly distributed load is best size in PU per unit. This is the value we need to calculate. Best size in per unit for UDL, uniformly distributed load. Please try to solve this one. Kind of similar, but given directly in the slide itself. So last one was the location, and this is the size. Okay. Last one was capacitor location, but this question is pertaining to the context of the capacitor size. So I think the screen is visible, right? Any idea what should be used as starting condition to solve this problem? Any idea? Otherwise, we'll start solving. Okay, let's solve. If you, in the meantime, if you find the answer, please write it in the chat box. Otherwise, we'll try to solve it. So since the is for the best size, okay. So with the aim of power loss reduction for a single capacitor, so del P L S can be directly obtained from the formula. Just keep these formula in mind because these questions might come likewise in the final exams too. No need to derive them because it would take much of a time, but
So for optimal, so we need to find the optimal value of C. Okay. So to find the optimal value of C, what we need to do is that del PLS by dC, and that should be equated to 0. And once we equate this to 0, derivative will be 1 minus 2C plus C square by 4. This is 0. So just 4 minus 8C plus 3C square equals to 0. So this would be, just solve this quadratic equation. 2C plus, so C can be, here it is 2, 3C common, is C minus 2 minus 2 common C minus 2. Yes, so one of the value of C is 2 and another will be 2 by 3. So in case of when we are trying to find the optimal value, so what should be the value of C? We have obtained two solutions for this quadratic equation. So in order to find the optimal value, what should be our choice? Please, if you can, chat box also write it. So we are trying to minimize our cost, right? So we need to find the optimal value of C. So each of these value of C will come with an associated cost. So if the value of C is 2, the cost will be like 2 only, because if the value of C per unit is much higher, the cost incurred or cost associated will also be very high. And so our choice here for these two cases will be to select 2 by 3 per unit as the optimal value, right? So optimal choice is 3, 2 by 3, sorry, which is equivalent to 0.66. Is it clear? Okay. So question two. In a capacitor used in distribution networks, some capacitors some capacitors are kept fixed and some are switched. Why? Option A is capacitors cause over voltage light loading. Option B is switch capacitor. Costly. And option C frequent capacitor switching causes transients and disturbances. So this is an MSQ question. Okay. So in a capacitor bank used in a distribution networks, some capacitors are kept fixed and some are switched. So why? So one only fixed capacitor cause over voltage during light loadings. Switched capacitor is costly, and frequent switching causes transients and disturbances. You may write in the chat box also. This is an MSQ type question. C. Yes, C is correct. MSQ, multiple answers are correct here. Okay, so not MCQ. C is correct. Anything else? Any anything else? Or we should move on to the next question. So switched capacitors enables and mixture of switched and fixed capacitors enables various, uh, or we can say, the ease of operation can be ensured from both the types of capacitors, presence of both. Because if we use only fixed capacitors, that will definitely cause over voltage during light loading conditions. Since the capacitor is fixed at a single place, there might be cases when the loads would be
at the different positions. Higher loads might be the different nodes. So in those cases, the systems may cause over voltages, and switched capacitors are costly also. So we cannot use only switched capacitors all throughout. So there has to be a trade-off, and for smooth operational, for to obtain a smooth operational behavior, switch capacitors cannot be single-handedly used because cost is also constrained. So both these types are used, and the three options are correct. All the three options are correct. Okay, so let's move on to a similar bunch of questions as we have tried to solve. These are kind of same, just the values are different, so that would yield a different result, but the procedures are same. Already we have discussed, so we can go through these questions very fast, right? Just solve. The question is, for this case, the question is, although it is not question C, so let me write it here only. Same type of question. Same type of questions. So we have already solved. These are just a variant with values being a bit different, but nothing else. A. Yes, A is correct. Just solve it very fast. So active power is P is equal to root 3 VL IL cos phi, and VL is given 11 kV. So root 3 into 11 into 10 to the power 3 into IL. IL is 320 here, and power factor is 0.65. So that would result in, I guess, 3962.93. Okay, that's that is the answer. Same type of question. Now the question 7. Determine the load demand in MVA. So apparent power is required to be found out here. Please do it very fast. You can complete 4 5 questions. Is it fine? 6.096 was the answer. Yes. Same type of questions. Let's solve first. Next question is question 7. Determine. After capacitor placement, what is the power factor? So after the capacitor placement, the power factor should improve, right? So previously it was 0.65. Now the load side current that we can observe, the current that we can observe, what is the value? This is the value of the current, right? 240 ampere is the current now. So the new apparent power will be root 3 VL IL. Let's say new will be root 3 into VL. What is VL? 11 by, okay, sorry, line voltage is 11 into IL. IL is 240. Let's let me tell you. root 3 into 11 into 240. 4572. And but active power demand is fixed. So we can say power factor is E by S. Yeah. So power factor, the power active power 3962.93. 39 is fixed. Divide by 4572.6. 3962.93 divided by yes. Yes. Right answer. Okay. Yes. You are correct. So mm, determine the capacitor bank rating. So previously we have solved in a longer procedure, which is the most obvious and deterministic procedure, but we can directly use formula. So the same type of question, so we will try to solve it now, but that will take much of a time in case of examination. So you can just remember or simple formula we have. A. Yes, A is the right answer. So previously we have solved in detail. So how we have calculated what will be the new value of Q, and accordingly what will be the capacitor value that should be added. The power factor needs to be how the power factor can be improved. So this is kind of same, but much shorter formula we can use to get the answer directly. So just use capacitor rating, or we can say C is equal to P tan phi minus this initial minus tan phi post. You can say pre or post here. So phi pre is cos inverse 0.65, and phi post is cos inverse 0.8667. This we have obtained as a new phi. So just place these three value here and these post value here. You will get the final answer. Okay. So QC will be P is given 3 to 3962.93. 3962.93 tan of phi 3 minus tan of phi post. Okay, so if you calculate, I think you will get the answer. It will be 2, 3, 2352.31. Can you please?
Uh, ac- Actually, this question is based on the power factor correction formula,
Yes,
right?
yes, 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 yes.
Sir, actually, one more question that is based on the power factor correction formula. I am trying to solve that, but I did not solve. Can you check? Just I share the screen of question.
Okay,
Can you
sure,
check?
sure, sure, Leonard, please. Okay, let me just then. Exit.
Sir, this is the question.
Okay. An industrial.
Actually, I want to solve a power factor correction formula, either any other formula.
Okay, okay. Industrial load 5 megawatt is installed and shunt capacitor rating to maintain the power factor and to lag. Capacitor goes out of service. What will be the power factor? Okay, 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 okay. So, I think just try it in. Uh, so you have mentioned capacitor remove. Yes. So, 5
So 5.3 to 5. But now you have mentioned that VAR is gone. So yes, service point previous power factor was 0.9. By 5.263. This is the value of S. Now 5.263 square minus P naught is 5.263. Okay, okay. Let me just complete this one. I'll solve it. Okay, we'll solve it together. Just keep this question. Just can you post this question here or
Uh,
okay? Just take a let me take a note of. Question. We'll just solve. I have two or three more questions. Oh, you can't copy it here, right?
Actually, I was trying, but I
Okay, no
can't
issue.
copy.
I'll just mm, okay, okay, okay. Okay, just you can. Your screen is, I think, sharing mode. So let me just complete this and we'll solve it. The next question was determine the, this was the ninth one, yes, this is the 10th question. Determine the magnitude of voltage drop of the feeder after capacitor placement. 800 volt, B is 1400 volt, C is 1000 volt, and T is 1200 volt. Just this is the magnitude, so please try to solve this. So anyone, so kind of similar question. This is the last one. So, okay, let's solve fast. Yes, D is 1200. Yes, D is the correct answer. D is the correct answer. Okay. So, okay. So just the voltage drop, you can see voltage drop is I Z magnitude, and I is, so after capacitor placement the current would be, so zero point 0.8 into 5, so it will be, feeder length is 5 kilometers, so zero point 0.8 into 5 means 4 square, and this is 0.6. The same values are kind of same to 240 into 5, so that will be 1200 volt. So this is the correct answer. So can you please share? So this is the, from my part. This is the final uh, discussion session. Final question. So can you please share the question once? Let's try to solve it.
Yes, sir.
I just write down the points so that, and then share my screen. So, okay. So industrial load is industrial load. Yes, visible. Industrial load 5 megawatt. Shunt capacitor is shunt cap UMR. Maintain the power factor at power factor 0.95 lakh. Capacitor goes out of service. If cap out of service. Measure power factor, find power factor of the industrial load. Okay, so I have, okay, the options. Let me write down. 0.72, point,
Sir, answer is B. Just answer is B, but just I have to check how to
The answer is given B. Right answer is B. Okay,
say.
got it. So let us solve it. 0.902 lakh. So okay, then no need to add this. Now let me share my screen. So initially it is given the active power is 5 megawatt. So P is 5 megawatt and Q is, or you can say QC is 2 MW. So what we can do, our power factor is given 0.95 lakh. So we can calculate S, apparent power. S will be P by power factor. Okay. So P by 0.95, 5.263, 5.263. This will be MVA. Okay. So this will be 5 point, but so this we have obtained. Now the reactive power we have used, reactive power. So net reactive power, net Q will be S square minus P square. So this is 5.263 whole square minus 5 square. So we take root minus 25, 1.643, 1.643 kvar. Sorry, m1. This is the m1. But what we have seen is that there is a two-member shunt capacitor connected. So this is when the capacitor is connected, right? So what we can see, this is when the capacitor is connected. Now the capacitor becomes out of service. So when capacitor is out of service, then the Q would be, so Q mu I can say, and this is old. So Q old plus QC. So QC will now become the total capacitive power that is required to be delivered from the source end, right? So this is Q old. Q old is 1.643 plus 2. So this will be 3.643 mR. So so now what we can do, we can calculate S mu, which will be P is same but Q becomes mu, right? So what will be the value? P value is P required is 5 megawatt. 5 megawatt is P. So 5 square plus 3.643 whole square. So 5 square plus 3.643 whole square. Root under answer 6.186. 6.186 MVA is the new MVA. So So, So this is the new MVA of when the capacitor is out of service. So power factor new will be P is fixed, but S becomes new. So P is 5 by 6.186. So 5 divided by 6.186. That is becoming 0.808 lakh. Is it okay? Yes, we can directly use that. So I tried to detail so that the understanding is clear. Yes, is it clear?
Yes, sir, it is clear, but it's a very lengthy process. I think we go with the
The same. But I tried to detail because you just asked me that.
correct,
What,
correct,
so I
correct.
tried to detail. So I've tried to go along step by step so that it becomes easy understanding. But
Yes,
you
sir.
can directly use as here it is mentioned in the chat box. You can directly use that. You will get the same answer. I
Thank
guess.
you, sir. Thank you.
Okay. Okay. Any questions? Or we can end this today's session now.
Yes.
Okay.
Thank you, sir.
Okay. Thank you. Thank you. We'll meet on next Tuesday.